Our next speaker is Lucas Ortiz, representing the PhD program in Applied Mathematics.
So imagine the problem of predicting the risk of a wildfire somewhere across the country into the future. As you can imagine, there's a lot of different factors that would affect whether or not there's a high risk of a wildfire occurring in a location, like the temperature at that location, the amount of humidity at that location, and the amount of wind. Now, all of those things are large data problems where the models that we typically use to predict those things into the future tend to be highly complex. So there's a challenge in trying to be able to predict what the future risks are in a fast enough way to be able to use those forecasts effectively. Because the data set, like the one that I'm working on, covers all of North America, you can imagine that trying to figure out what's going to happen 3 days in the future using this entire domain of data is going to take a lot of computational time. And then once you have moved forward and actually gotten a sense of what the risk is, you're not even done because you have to run an additional step of modeling to figure out, will we actually have fire starts occurring? And so the problem is you have this massive data set, you need to use it as quickly as possible, and how do you actually incorporate what you know about the data to be able to do that faster? That's the problem I'm working on. Our approach comes almost entirely from the statistics side of things. And so what we do is simplify the way that we conceive of the model, right? Instead of running a complicated climate forecast into the future that may take a long period of time and be a very complex model, we look at a very simple model and maintain predictive accuracy and speed by picking out the right things in the data set to use. Not everything matters as much. There's certain things that matter more within the data. By picking those things out, we're able to more effectively do this prediction. For instance, one of the things that we're able to use is the cyclic nature of temperature. And it turns out that because of that periodic nature, where it goes up at one point and down at another point, you can simplify and work with that to be able to do things much faster. The result of doing that is that we have done the preliminary work to show that we can potentially get as much as a 90% time reduction in knowing what the risk will be in the future. The advantage of that is that now you can run potentially 10 times as many models in the same amount of time and get more information to be able to use to get a better idea of what the risks are. And that's my thesis in a nutshell.
Any questions? All right, thank you.